Xpress Optimizer allows the user to read and set global and problem-related controls, and to read problem attributes using its Python interface. A control is a parameter that affects the performance of the optimizer and can be both accessed and set by the user. For example, the optimality gap target, the feasibility tolerance, or the specific algorithms applied by the solver are examples of controls that can be either read or written to. An attribute, on the other hand, is a property of an optimization problem, and examples include the total number of rows or columns of a problem, or how many quadratic elements have been identified in an objective function. Attributes can only be accessed for reading, as their values cannot be explicitly modified by the user. For a full list and description of all controls and attributes available, check chapters 7 and 8 of the Optimizer Reference Manual, respectively. Every optimization problem has its controls object, which can be both read and written to by using problem.controls followed by the control name, which can also be used to set a new value for the control in a new value is assigned to it. The functions getControl and setControl from the problem class refer to this object. Examples of using problem controls include querying the problem's feasibility tolerance, setting its pre-solve status, or assigning a new value for the relative optimality gap tolerance for MIPs, which is calculated from another problem's control value in the last part of the example. Keep in mind that the values of controls have a double-digit precision, and their type can be integer, floating point, or string. An important problem control when solving mixed integer problems is the heuristic emphasis control, which instructs the optimizer on the use of heuristics in the early part of the search and can have a significant impact on the solver performance depending on the problem at hand. This control can be set using p.controls.heuRemphasis, and its default value is equal to -1, which applies the default balance strategy. While assigning it a value of 0 disables all heuristics, assigning values 1 or 2 will trigger the increasing use of heuristics, aiming to reduce the primal dual gap early on in the search, typically at the cost of an increased time needed to prove optimality. Therefore, this control must be tuned to serve the purposes of the use case. For applications where finding a high-quality solution quickly is more important than proving optimality. Xpress Optimizer provides a built-in tuner that attempts to discover better control settings by experimenting with different combinations of possible control values. The tuner can be applied to a single problem or a collection of problems, and each tuning run will involve solving the problem between 100 to 200 times. Therefore, keep in mind that using the tuner can become computationally expensive for larger problem instances. There are controls related to the tuner that can be set by the user, such as the maximum time, in seconds, spent in tuning, or the number of threads to be used by the tuner. Problem methods directly associated with the tuner are also included by the Xpress Python interface, such as those for reading and writing XTM files with the current tuner options set, and the option to tune the problem as a certain problem type, LP, or MIP. The tune method finds the best control settings configuration, which is then applied by the optimize command. Explore the method problem.tune for more information about problem tuning. There are two types of controls: global controls and problem-specific controls. Global controls are controls that apply to all problems included in the Python program and can be read and written to in a user-friendly way by calling xp.controls followed by the control name for reading, and by further assigning a new value for writing. Global controls will be initialized at their default values when importing the Xpress package. Examples of using global controls include checking whether pre-solve is turned on or off, checking the current setting for the popular heuRemphasis control, or setting a new feasibility tolerance value. Problems have their own attributes object, which stores the features related to the optimization problem by using problem p.attributes followed by the attribute name. Contrary to controls, attributes can only be accessed for reading. Problem attributes are available after a problem has been created or loaded from a file. Examples of using problem attributes include querying the node depth, the number of irreducible infeasible sets, or the relative optimality gap tolerance, printed as a percentage in the last of the examples shown. The Python notebook named callback_new node showcases the use of problem controls, along with Xpress callback functionality. In this example, a problem is read from an external file, and a callback function is used to store information for every node of the branch and bound tree during an optimization run. The run is stopped after a predefined number of nodes have been explored, and all nodes explored during the tree search are plotted after the solve. After reading the problem and properly declaring the callback function, two controls are set. The first control, named maxNode, limits the maximum number of nodes that are explored in the tree to 10. When exploring nodes using multiple threads, this limit may be slightly violated, as it does not represent a hard limit. To ensure that parallelization does not hamper the maximum number of nodes to be branched on, we also set the threads control to 1 to limit the number of threads to a single thread, effectively ensuring that the max node limit is fulfilled when searching the branch and bound tree. After running all code cells, the output plot at the bottom shows that exactly 10 nodes of the tree have been branched on as specified, further validating the effectiveness of the controls we have set. Other controls that affect the stopping criteria of the solver can be applied. A commonly used control is the MIP rel stop control, which determines the minimum optimality gap accepted to terminate the search. For example, by setting MIP rel stop to 0.3, meaning that the user accepts a solution within 30% of the optimal solution, we verify that fewer nodes are explored by the optimizer.